Hello, it's Mr. Colati, and today we're going to be going through 7.3 Kirchhoff circuit laws. And this is the first section that extends beyond what we learned in grade 9, and it can be a little tricky because we're going to be doing circuit analysis. So let's first go through the Kirchhoff current law. So Kirchhoff was the name of a scientist who kind of figured this out. Kirchhoff's current law states that for any node in a circuit, all the currents coming in has to be the same as all the currents going out. They have to balance. Remember in my analogy, current is like a river flowing. So all the water coming into this point is the same as all the water going out. We can look at how this applies to two types of circuits that we've learned, the series circuit and the parallel circuit. In a series circuit, the river is basically flowing in one path like this. So the current is always the same. If I look at any node, the current in is the same as the current out. So this is easy. For a parallel, we have all these different paths. So you have to imagine this big river that's flowing here all of a sudden divides up. Some of the current goes here, some of the current goes here, some of the current goes here. But whatever current goes into this point, so coming in, has to equal the three currents coming out. So if I have 9 amps going into this point, then this could be 3, 3, 3, or it might be 1, 5, 3. There's lots of different possibilities. And then they all meet up again. So the river breaks up and then it comes together again. That's how the current law works. So let's look at the example. Down here I have 12.5 amps on the main stream of my circuit, right? That's like the river. And then what do I see here? Well, I have 2.5 going this way, and it's hard to see here, so let's write 2.5 amps. I have 4.0 amps here. So the question is, what do I have here? Well, we know from KCL that I0 is equal to I1 plus I2 plus I3. All the current going into this point, this node here, has to be the same as all the current coming out. Now I can fill in my blanks. 12.5 is equal to 2.5 plus 4.0 plus I3. This gives me 12.5 minus 2.5 minus 4 is equal to I3. So I get I3 is equal to 6.0 amps. Now, in time, as you do more of these in practice, you might be able to just write 6 here. You can almost do it by inspection, by looking at the circuit. But I want you to understand exactly how it comes from. Okay, let's turn the page. The second of Kirchhoff's laws is called the Kirchhoff voltage law. And this one's a little bit more confusing. It states that for any loop, the voltage has to equal the voltage from my source has to equal the voltage from my loads. So for this loop, if I look at a series circuit, my battery is a voltage source, so that gives my electrons. Remember, voltage is all about money or height or amount of juice that they have. So the electrons get a lot of energy from this battery. That's a voltage source. And then they spend that voltage at each of these loads or light bulbs on their path around this loop. When they get back to where they started the battery, just before they go through it, they have, you could think of as 0 volts left. They've spent it all. So there's a few ways, again, to look at this analogy. You could think of the battery as being the parent, so they're giving money to the electrons. So say they give 20 bucks to the electrons. Well, then as the electrons travel on their trip, they spend money at each of these stores. So they spend $5 here, $10 here, $5 here. And then they come back, they have 0, and they get more money from their parents. How do they know how much they spend at each spot? Well, it has to do with the resistance of each lamp, which we'll get to see as we go further on. But that's kind of how circuit design works. Another analogy is that this is a pump, a water pump. You've pumped the electrons really high, and then as they travel around this circuit, each of these is a little drop. And so they drop and they drop, and by the time they get back here, they're all the way at the bottom of the lowest point again. So voltages in series through Kirchhoff's voltage law, this voltage is equal to this plus this plus this. Now, conversely, if I have a parallel circuit, look what happens. Well, if I draw loops, there's a lot of different loops here. There's a loop here, there's a loop with this leg, and there's a loop with this leg. Each electron, when it leaves home, remember, let's use the money analogy, it leaves home with $20. It can only travel one path. So this electron leaves home, and it happens to travel this first path. So it has to spend all $20 it received from its parents at this load. It doesn't have any other loads it visits. Another electron might go this path, and so it spends all of its money here. And then again, there's a third option where we go down this last path. We spend all of our money there. So the source voltage, or the battery voltage, is the same then as the load voltage, or whatever's across this parallel circuit. So this is equal to this, is equal to this, is equal to this. This is a little bit more of a confusing concept. I'd like to use the money analogy and drawing loops. So let's do a few examples here and we'll see how it goes. Calculate the voltage V2. Okay, well, I can do a loop here. I'll draw a little picture. Well, get out a highlighter, I'll draw my loop. Remember, this is usually we flow from positive to negative, right? Conventional current. So my loop, well, there's only one. Right? I can't do any other loop. This is a series circuit. So we know that my sort by KVL, my source voltage, VO, has to be equal to V1 plus V2 plus V3. Now I can sub those values in. 2.4 times 10 to the 2 is equal to 80 plus V2 plus 60. Again, now we're going to be getting quicker at this as we go. So I have 2.4. It's hard to see. Is that better? 2.4 to the power, or 10 to the 2 minus 80 minus 60. And I get 100. V2 is equal to, I think it would be 100.0 volts. So again, you have 240 volts when you leave home, and you spend 60 here, 80 here, so therefore you must spend 100 here, because you spend all of your money. Okay, so now let's combine these two concepts with some the first day of circuit analysis. So here we have a circuit, we know a bunch of things, there's a lot we don't know. What do you want to start with? I usually like to start with current because current is the easier one in my opinion. So let's look what we have. Oh, we know this one, we know this one. Okay, let's start here. So I know that 4 amps comes out, 3 amps goes in, and here I don't know what it is. Well, you should be able to figure this out, right? Again, by inspection. Now, why don't we write it out for now, but the next one we'll skip some steps. But by KCL, I3, I1 is equal to I2 plus I3. Sorry, that's hard to read. So 4 is equal to 3 plus I3. So I3 has to be 1 amp. Okay, so 1 amp. Let's write that in. Now, if you chase this backwards, well, 1 amp, this is still 1 amp, right? It came out as 1 amp, and then this is 3 amps here. So the question is, what's I4 here? What's this amount going in? Well, by a similar logic, I4 is equal to I2 plus I3. I4 is equal to 3 plus 1. I4 is equal to 4 amps. Okay, so that's current. Now let's look at the voltage. And again, the easiest way I find to do this is to draw voltage loops. So let me draw one. Okay, so if I was an electron leaving home, I could follow this path. That would be my one option. And let me get my yellow option, my other option, which would be this. You don't have to draw this, but just for our example, I find it is helpful. Okay, so let's look at this. Now, what are my loops here? Let's look at the KVL. So I would have VO, so that's what I started with. That's the money leaving home. And then I would have V1. Let's do the, what are we doing? The blue. Sorry, let's do blue first. So V1 plus V2 plus V, sorry, this is V4, V2, V1. So V4, V2 plus V1. It's going to be hard to read, right? This is V1, this is V4. Okay, and now let's fill in the numbers. So I have 18 is equal to V4, we don't know what that is, plus V2, we don't know what that is, plus 6. I'm kind of stuck here because I have two unknowns. Let me look at my other loop. Maybe there's more information there. So again, by KVL, I have VO, so we're doing which loop now? The yellow loop. So VO, okay, pass through this store, this resistor, so that would be V4 plus V2. Oh, that's V, oh boy, that's really hard to read. This is V3. And then we have V1. I can fill in my numbers. I have 18 is equal to V4 plus 3 plus 6. There we go. So this one actually I should have done first. I can solve it first. So V4 is equal to 9. Now once you know that, well then you can go back up here. This is now 9. So then you have 15, V2 is 3 volts. So we sub in. So you don't get a situation where you have to solve two systems at the same time, but you do get a situation where you have to solve one loop first, right, in order to find the other ones. Basically, we couldn't do the blue one because we didn't know, there were two things we didn't know. The yellow one was more useful. It's no surprise that V2 is 3 volts because we know from the Kirchhoff's law that parallel voltages are the same. So this is 3 and 3. But I do find going through loops is easier, right? Or it is logical. So 18 volts, $18 you left home with, you spent 9, you spent 3, and then you spent 6. So you spent all of your money. Okay, let's try doing this last question, and this time we're going to try kind of doing it a little bit more by inspection. So let's look. We have, let's again start with current. That's my favorite one to work with. So here we have 5, and then we have some unknown. Okay, and we don't know how much is here. Okay, let's look what we have. Okay, so this looks like a good node here. So I have, again, I can draw 2, 4, and an unknown amount. So 2 plus 4, so I1 has to be 6. Because those combine to form 6. Now that current is the same everywhere in this series section. So this is still 6 here. And then we know that 5 of it goes this way. So this must be 1. So that is I4 is equal to 1 amp. And then the 1 and the 5 recombine to form 6, and then you have 2 and 4. So great, that's okay. And now let's look at the voltage. Okay, so again, we could draw loops maybe to help us understand this. Let's look for a loop that has one unknown. So 72, okay, so both these voltages are unknown. Okay, then this voltage is known. And okay, so let's look at this loop. Let's go like this. So I have $72. I spend some of it here, then 20, then 36. So what are we solving for? V4 is equal to 72 minus 20 minus 36. That's 56. So 16. 46, 52, yeah. Okay, so 16 volts is this unknown amount. Now, the rest we could figure out pretty quickly. Because these are parallel and there's only one resistor, then we know that V5 has to be the same, has to be 16 volts. If you wanted, you could draw another loop and figure it out. So there's a path that would go like this. Okay, then there's another path where you go through either of these, and then you go through V2. Now again, it's no surprise, V2 is parallel to V3, so this has to be 20 volts. Okay, now we're just going to continue. So that's our lesson on KCL and KVL. There is a tricky homework page to work through. And I also want to revisit what we did last week, which was about Ohm's law and resistance. Remember, we learned this fundamental relationship between current, voltage, and resistance. Well, now we can revisit this question at the bottom of the page. This is where we take it to the next level with circuit analysis, because now you can find V and I using your Kirchhoff law, but then you can use two of these to find resistance. Basically, the strategy here is if you know any two things, you can use Ohm's law to find the third. So, for example, I already know V1, I1, and R1. So, by Ohm's law, we know that V1 is equal to I1, R1. So then this is going to be 4 times 10. This gives me 40 volts. So I already know this is 40. Maybe it helps to draw this in. Where's V1? Ah, here we go. 40 volts. We know 3 is 30 volts. And we know my total, or what goes across what I started with, was 90 volts. So now you can see that I could use KVL to solve this unknown voltage here. V4 is equal to 90 minus 40 minus 30. If you want to see that as a loop, so we have $90 we start with, we spend 40, we spend 30, we spend the remainder here. What is that remainder? It's 20 volts. So this is 20 volts. And we can write that into my table here. Ooh, what about V2? Well, I could do another loop, or I can remember that because these are parallel, they have to be the same. In terms of current, I only know the current at I2. So I only know that the current here is 1 amp. I don't have a lot of information about current. However, oh, we also know that 4 amps is here. Well, that's enough information for us, because we now know if 4 amps is going into this node, 1 is coming out, then this has to be 3 amps. So that is I3 is 3 amps. I'll just write that here by KCL. I3 is equal to 4 minus 1 is equal to 3 amps. And then when we come back together here, this is going to be 4 again. I mean, you could have seen that by knowing that all of this is the same current. 4 amps. So we're going to put a 4 here and a 4 here. And now to find the unknown amounts, you have to use your Ohm's law. So we have V2 is equal to I2 R2. So I get R2 is equal to V2 over I2, which is 30 divided by 1, which is 30 ohms. And we can continue in the same way, right? So I would have 30, etc. So 30 divided by 3 gives me 10. 20 divided by 4 gives me 5, as you can see. Oh, and 90 divided by 4 gives me 22.5. So there you go. That's your first first real kind of circuit design. And look how somebody designing this, they can't really control the current. Or, what they can do is they can control the battery size, they can control the resistances. And then by doing this design, they can ensure that the voltages and currents are what they need. So if you have a light bulb that goes on at a certain current or a certain voltage, you can ensure that you've got the perfect amount. So that's how circuit design works. You can see that the resistances do cause this. That's the real reason why the currents are different in these different legs, right? Why does this one have 3 amps versus 1 amp? Well, this has a 30 volt resistance, this has a resistance of 10 ohms, whereas R2 has a resistance of 30 ohms. Remember, resistance is it resists current. So when the river flows up here, well, this has a much more resistance, so a lot less current flows down. More of the current tends down the lower resistance path. Okay, good luck with the work from there's homework that goes with this section as well. Good luck with all this circuit analysis, and we'll see you next time.